Right, we've got a couple of these problems for moment of inertia. Now what we're doing here, it's a two-step process. The first thing we got to do is find the y-bar centroid, and then the second thing we have to do is find the moment of inertia about the centroid. So it's a two-step process. We've got two of these to do, 322 and 323. We got questions on either one of these in particular? We could run through one of these, maybe. We could look at 323. We'll look at that. Right? So 323, we've got three rectangles put together, two flanges and a web. So I want to get set up to do the work first. So I want to get the areas of each one of the three pieces, the top flange, the web, and the bottom flange. And I want to find the distances from the base of the beam to the centroid of each one of those shapes. So that's what I'm doing right there. I've got the areas on the left, base times height, and then I've got the distances from the base to the centroids. And remember, you're measuring those distances from one line, typically at the base of the beam, when you're looking at the cross section. So half a 2's 1 inch for the first distance. You go 2 inches up and take half a 10 to the second distance, and then you go 12 inches up and take half a 2 for the third. Okay? So the distances are 1, 7, and 13. So once you have that information, you can start to fill in the tables that you'll need to fill in to figure out the y-bar centroid, which is the first thing you want. Then you want the moment of inertia. For both cases, you need both areas and distances. So I get that all lined out. So we all right with that? All right, then I want to find y-bar. So what I do for each part, so I've got the top one, Roman numeral 1, the web is Roman numeral 2, the bottom flange is Roman numeral 3. Take the area times the y-bar distance, multiply them together, and I get y-bar A. Looks like I forgot to put an A in there. Y-bar A. So 24 by 13 for the top one is 312. 20 by 7 for the middle one, the web there is 140. 12 by 1 for the bottom one is 12. Then what I do is I add up all the areas. I get 56. Add up all the y-bar A's. I get that value. And then I take the sum of the y-bar A's and divide them by the total area, and I get about 8.29. One thing I would do with that number is just look at it, see if it looks about right. Ask yourself if you tried to balance that was a shape cut out of cardboard or something, and you flipped it horizontally and tried to balance it on your pencil. Would it balance there? Looks about right. Okay. Because the top flange is bigger than the bottom one, so that'll pull that centroid up a little bit. Okay. So that's where the y-bar is. That's where the centroid is at. And that line extends down the length of the beam, making up what we refer to as the neutral axis. Okay. So we got something like that. All right. And so the y-bar, that runs down the length of this beam like that. That's the neutral axis. Okay, we good with that? All right. Now the next thing we want to do is find the moment of inertia about that axis. Okay. So what I'm going to do next is I'm going to find D, because what I'm doing here for my finding the moment of inertia, I got to take I bar plus AD squared. I have to do that. So I need that D distance. Now what that is the distance from the centroid, which is at 8.286. So that's the neutral axis, basically. I'm going to go from there, the centroid of the entire beam, which I'll call the neutral axis. From there, I want to go to the centroids of each one of the pieces that make up the shape. So what I'm finding here are these distances here. I'm finding that distance that distance, and that distance. So what I'm doing there, I'm taking the height of the centroid of each one of the pieces, I'm subtracting off the neutral axis dimension there, and that gets me the offset distance, which I call D. Calling that dy there, not like a calculus dy, I don't mean it in that sense, I just mean a distance measured in the y direction. Okay? So I'm getting 4.714, 1.286, and negative 7.286. Now, I got signs on those. A lot of times people don't even bother with them because the formula is AD squared. Those signs just square out anyway. Doesn't matter, but I'm just putting them on there because that's really what they are. So we good with that? Doing all right? Okay. All right. Now I just put together a big old table, and I'm going to do for these rectangles bh cubed over 12 plus AD squared. That's what I'm going to do, because what I bar is for a rectangle, what I've got here is that my total I is equal to bh cubed over 12, which is the moment of inertia of a rectangle about its own centroidal axis. And then I'll add in the AD squared. So I'm just going to set up a table that has a column for bh cubed over 12, a column for A, a column for D, a column for AD squared, and then a column for the sum of them. Okay. So I just set up a table like that. So part number one, I got a base of 12, height of 2. So 12 times 2 cubed over 12 is 8. That's inches to the 4 is the units on that. The area is 24. The distance is 4.714. So I take 24 times 4.714 quantity squared. I get 533.3, and I add that to the 8, and I get 631. And I just run through that process repetitively. The second one has a base of 2. The base is parallel to the axis, so that would be 2 across, parallel to the neutral axis. The height is 10. So that's, I'm looking at the web. So 2 times 10 cubed over 12 is 166.7. Got the area times the offset distance squared is 33.1. Add them up, and I get 200, pretty close. Okay. And then the last one there, the base is 6. Okay, base is 6, height is 2. 6 times 2 cubed over 12 is 4. Area is 12. 6 by 2 is 12. Offset distance is 7.286. I square that, multiply it by 12, I get 637. Add it to the 4, I get 641. Add them all up, I get 1382 inches to the 4. Okay. So that number represents the amount of stress that will build up when you apply a load on that beam. The bigger the number, the less stress you'll have that builds up. So that's a big part of being able to design a beam. So for this homework, and for homework in the future when we use this in the final, you're going to want to be able to generate these tables and calculate these values and run them through. So this is a process, you know, it's not like something you got to scratch your head and figure out. It's more just to do this, do that, do that. And that's how you want to prepare for it, you know. Be sure that you know how to build one of those tables and what those values are and what they mean, okay? Because we'll be doing this a fair amount as we do our beam analysis and all that. As we're going through this stuff, I'm sure it'll be on the final and all that. So, okay, I want to get comfortable with it. All right, now, is that good on that one? We're good? Okay. Now, the one previous, I do want to point out one thing about it. You know, this involves a fair amount of numbers. This other one, just, you know, they all do. This is an actual beam. You know, it's a W, I don't know what the heck it is, but it's a W 30 by 211. So remember to answer these questions here. I want to be sure that you know what those different values stand for. So what does W stand for? What does 30 and what does 211 stand for? Now, the other thing is I've had people run numbers and calculate Y bar and burn a fair amount of time and energy doing that, but it's not at all necessary. That's symmetrical. Centroid's in the middle, okay? So don't bother putting together a whole table. You don't really need it. I mean, it's just right in the middle. It's where the centroid is at, okay? Now you can calculate it with a table and hopefully you'll come up with that, but, you know, just be aware of that. And then the other thing is, if you look at where these centroids are at, there they are. So just 1, 2, 3. Now the neutral axis there runs through the middle centroid. Okay. Now when you're doing that's the neutral axis for when you calculate Ix. Now when you do the neutral axis for the other one, which is Iy, it runs right down there, okay? Right down the middle. So that's the neutral axis for Iy. Now what you notice is all three of those centroids of the parts line up right on that axis. And that means that all three of the d's are 0. Okay? So that doesn't involve a transfer axis thing. You do Iy. Everything's right on there. You don't have to do the AD squared for when you do Iy. Now you certainly have to do it when you do ADX, but not Iy. Okay? You certainly have to do it when you calculate Ix, but not when you do Iy. That's what I should have said. Okay? So just remember that. So just remember the centroid is in the middle, so you don't need to go through a bunch of calcs on that. It's just half the depth. And then for Iy, you don't have an AD squared term because all the d's are 0 out. And remember to tell me what W stands for, what 30 stands for, and what 211 stands for. Okay. Good with that? Good. Yeah, question?
Yeah, for the table,
I'm sorry, now?
For the values listed in the table part.
Oh, I actually ended up dimensioning it for you. That's an old problem statement. Oh, okay. No, I guess I didn't. All right, let's, yeah, that table. So the question is, how do you find the table? I think I've got that thing. I'll put up a link in Moodle. How's that? I'm pretty sure it's already there, and I'll put a link in there. You know, these things are standard beams, so they have tables that just describe their properties. So I'll get a link up in Moodle for that if there isn't one there already.
We found like a table online that can use the
Yeah.
values from there.
Yeah, right. Yeah, and I'll have a link there if you need. Yeah, but there's a few of them commonly available. You know, all the mills make the same shapes. It's just kind of stone. Okay. All right. Call it good.